Alright, so we'll be starting off with the first law of thermodynamics today. So first law of thermodynamics, we talk about Q equals delta U plus W. So we apply this to a system, and the sign convention that we have is, we have thermodynamic sign convention. Think of it like this. Why does a man create a system? For example, why do we have a motorcycle? So that the motorcycle can give ride to us, or you want to push the motorcycle. Obviously, you want to give the motorcycle, you want to have a ride in that. So that this motorcycle does work for you, it is positive. And if you have to push it, that is negative. Work done by the system is positive. Work done on the system is negative. Okay? Take anything. Maybe you have a ceiling fan. If the ceiling fan, it rotates for you. If it does work for you, it's positive. If you have to push it and rotate it, that will be negative. So work done by the system is positive. Work on the system is negative. That's the convention we are going to use. Then as regards the heat transfer, Q, what is the deal that you have with the motorcycle? Even a new motorcycle, you will have to give petrol. When you give petrol means you give heat, and it should give you work. So giving fuel or giving heat to the motorcycle is positive. It is the correct part of the deal. If your motorcycle gives a lot of heat, sound and fury, bekar hai. Okay? If something which produces a lot of sound when riding, if your engine roars, it's a bad engine. If it hums, it's a good engine. It should produce less sound, less heat energy out of it. So heat given by the system is negative, heat taken in by the system is positive. Okay? And delta U of course will be final energy minus initial internal energy. So we have that sign convention in place. Q equals delta U plus W, like that. Okay? So now this is exact, in chemistry also you have, so don't kind of confuse it. That is a separate thing. So can I can one of you summarize it for me? What is it? What is the convention that we are following? Work done by the system is? Work done by the system is what? Yeah, work done on the system is? Negative. Yeah, heat given to the system is? Positive. Positive. Heat given by the system is? Negative. Yeah, that's it. And delta U is change in internal energy. Final minus initial. That's the convention we'll be having here. Q equals delta U plus W. And rather, we could write this formula alternatively in this format. Del Q equals du plus del W. So this symbol we are putting to show that Q and W are path functions, and U is a state function or point function. So Q and W are path functions. So that will depend upon initial and final path. For example, what's the path function? It will depend upon the way you take. For example, the distance of your school from your home will depend on how you want to go. A shortcut, long cut, you could have a circular route, whatever. So you can make the path as short or as long as you want. Okay, as long as you want, but not certainly shorter than what it could be. So del Q, whereas this is the state function, the point function, like a height. Now the height of a, for example, I do not know which floor you are studying in. What floor is that where you are sitting? Is it a ground floor, first floor, what? Basement. Huh? Oh, it's a basement, oh God. So I was totally wrong. So you are in the below the earth. Okay, so your height is negative so and so. So for me it doesn't, I don't have a sense of how I can find out, and it doesn't matter. So, and no matter how you measure the height, for example, if you are on the second floor, if you measure the height with a rope, or you measure the height by the staircase or by dropping a stone, no matter which way you measure the height will be the same. It doesn't depend on the path which you go from one floor to another floor. So delta U is a state function. So to indicate that, we are putting this symbol. Later on I may not put that symbol. Just to begin with, I'm putting those symbols to indicate that. So let me write that as this is the path function, state function. We have that. Then further, now if you take the gas, if you consider the gas, here is a piston, and there's the gas inside the. This is the gas here. So, if this piston moves by dx, and the cross-sectional area is A, so the small work done will be P into A is the force and dx is the displacement. So the work done by the gas can be expressed as P dV. dV is the change in volume that when the piston moves back, that much will be the expansion of the gas. So we call the elemental work done by gas dW equals P dV. When we normally say work done, it is work done by the gas. In thermodynamics, we're talking about the gas. You might have work done by certain other agents, then accordingly you have to look into it. And I'm not saying W equals PV, I'm saying dW equals PdV. That's true. Thereafter, now we'll look at various processes. See, if you talk about in thermodynamics, there are infinite number of processes, but we will only talk about a few of them which are kind of famous and have a feel of it. For example, there is if you want to go around Delhi, I believe there is you can buy a ticket like Delhi Darshan, etc. So you buy a ticket and in the morning they take you around and show you all the Rajghat, Vijaygarh, etc. Then India Gate, Birla Mandir, Qutub Minar, and by evening you are off. By 4 o'clock you claim that you have seen Delhi. You have a checklist there. But there are people living in Delhi for 50-20 years and they also know Delhi. Now you cannot claim to know how come by within 6 hours you have known Delhi, and there are people sitting for 15 years and they say they still must be seen in Delhi. What do you mean by the two? Well, somebody who's been lived there for a long time will know each nook and corner. Okay? For example, I don't know, when I was in Delhi, this supply chart wala was very famous, UPSC. You had a famous chart shop. Now I do not know you still know that or not. So now that is something which is not written on a tourist guide, but it is very well known by somebody who knows comes to Delhi. Now that's, you have an intricate point. So it may not have some label on it, but still it is very much part of Delhi. Like that, there are processes which don't have labels, but they are very much part of thermodynamics. Now, if you want to know thermodynamics intricately like that, then that's called a BTech course in mechanical engineering for 4 years. Otherwise, what we'll be doing is the short one, which we're going to do today. So we'll take a quick tour of thermodynamics, so to say. So several processes I'll show you, and I'll guide you through different processes. So let us see. So first of all, you kind of see each process and note down what are the properties. Then later on we'll integrate them. You'll have a look at various processes. Don't try to find what is the connection between them. There is no connection between Qutub Minar and India Gate. They are just different points of view. So like that, just have a tour first of all. Later on we'll try to make out the meaning out of it by making a chart. So here we go. The first process I want to show you is called the isochoric process. So when you say isochoric process, it means volume is constant during this process, which means dV is 0, which would mean dW is 0, and further W will be 0. Now when I say dW is 0 and therefore W is 0, now the reverse may not be true. If W is 0, is dW 0? Because if dW is 0, when you integrate it, its work done will be 0. I'm saying if W is 0, does it mean dW is 0?
No, sir.
Because you could have done positive work one way and an equal amount of negative work the other way, so sum of it will be 0. So that doesn't mean elemental work everywhere was 0. Okay? So dW is 0 implies W is 0. Now this is so in isochoric process. And further, if this be so, we can say from FLT, since Q equals delta U plus W and W happens to be 0, we will say Q equals delta U. That's the isochoric process. Each of these properties have a look. The challenge would be, right now I'm saying isochoric process has these properties, but later on, if you are shown one of these properties, you should be able to infer that this is an isochoric process. in the problem when it comes, it won't be mentioned it's an isochoric process. Once in a while it might be. But one of these properties will be there. And you kind of infer that, oh, it's isochoric process and all these things will be valid. Let's see further. We talk about the molar specific heat at constant volume. I think we talked about this in kinetic theory of gases also. But let us say this. This is the formal place where we talk about it. Molar specific heat as such means 1 by n dq by dt. Heat required to raise the temperature of 1 mole of a gas by 1 degree centigrade at constant volume. That we show by writing a subscript there. The subscript V means it is happening at constant volume. Then, but what is more important is, because when the process is isochoric, dq happens to be equal to du. So we rather say it as 1 by n du by dt. Now that is an important idea. This we had talked about in kinetic theory of gases as well, but there I mentioned it, here I am kind of deriving it. Now we say du by dt at constant volume, but to say du by dt at constant volume has not much meaning. It's like saying the height of the second floor as measured from the staircase. Why do you have to say as measured from the staircase? No matter how you measure off, the height is the same. As measured from the window will not be different from as measured from the staircase or as measured from wherever else. So the height is difference of 2 points. That's a state function. Doesn't depend upon the process. So I'm writing V and then I'm cutting it off to show that it is irrelevant in this scenario. So rather, this is a very important formula. du equals ncv dt, or rather we say delta u is ncv delta t. This is so for all processes. Although I have derived it using the idea of a constant volume process or an isochoric process, it is true for any process. Isobaric, adiabatic, isothermal, or whatever be the name. Delta U is always NCV delta T. Okay? Then, further, how do we draw a PV diagram? Just like a doctor uses an X-ray. For a bone doctor, he looks at the X-ray and can make out where the fracture is, etc. So he can read an X-ray. Likewise, a thermodynamics engineer looks at a PV diagram and understands the processes. So it makes the process visual for us. So this is called an indicator diagram. So how do you draw the isochoric process in this case?
Line parallel to T.
Yeah, that's right. The volume will remain constant. A vertical line shows an isochoric process. Right? And further, now in thermodynamics that we are talking about, we talk about the state variables. Any situation in which the gas is can be represented by certain variables like pressure, volume, temperature. There are many more: enthalpy, entropy, Gibbs energy. But we are not dealing with that. In our physics, we're only going to deal with pressure, volume, temperature. That's all. Not even entropy. In chemistry, you might be doing it. We'll just deal with these three. And we know that here, two of them are independent, because if you know any two of them, we can always find the third one using the ideal gas equation. PV equals nRT. These are some of the supporting equations which help us to derive all these properties of various processes. So I'm putting them on the right column there. Also, can you give me what is the differential form of the ideal gas equation? That's right. Differentiate this with respect to temperature. You get P dV by dt plus V dP by dt equals nR. This dt you can transport on the other side and you can have this. P dV plus V dP equals nR dt. That's the differential form of the gas law. All the gases that we are using in our course will be ideal gases, and the equations on the right will always be true for all of them, irrespective of the processes. And if there is a process, these properties will be useful. We can see that. Then, so we have looked at the isochoric process. We are moving on to the next process, namely the isobaric process. Isobaric process, pressure is constant, in other words, we can say dP is 0. What is the elemental work done by the gas? This is the formula. If you want to find out work done, we integrate this. Now we say we integrate from V1 to V2. Very often, 1 means initial, 2 means final. Now since pressure is constant, P can be taken outside and we get P V2 minus P V1, or we can say P delta V. That's the work done. Also, alternatively, using the gas law, we can say PV2 is nRT2 and PV1 is nRT1. We can say like this. This is also the work done in an isobaric process. Delta U, well, happens to be the same as always. Delta U is NCV delta T. I did not repeat it, but I'm just saying to confirm the formula. Okay, CV. Always so. We derived it once and that's all forever. And then we talk about Q. In the previous one, we defined CV as 1 by N dQ by dt, or for isochoric process, Q isochoric, we will write it as NCV delta T from the basic definition of CV. Similarly, what will you write Q isobaric as?
NCP delta T.
That's right. NCP delta T. So you can write like that or you can write it like this. NCP dt or Q equals NCP delta T. I'm writing both. Sometimes we use a differential form or the complete form. Okay. Then we have got our Q. I missed out something in the last previous isochoric. Just note that down. In isochoric, what is the state variable relation for isochoric? State variables relation for isochoric process will be P1 by T1 equals P2 by T2 because volume is constant. As pressure increases, temperature also proportionately increases for an isochoric process. That's what we write for isochoric. Write it down and write a similar equation for isobaric as well. So I'm rubbing this off and writing the one for isobaric now. So for isobaric, what will be the state variable relation? It will be V1 by T1 equals V2 by T2. And then finally, what is the PV graph? Indicator diagram, PV diagram. If your isobaric process is there, pressure is constant, we draw a line like that. If I put an arrow like this represents an isobaric expansion. The volume is increasing from less to more. If I put a reverse arrow, it would mean isobaric compression. Okay? Then, we are going to derive something called the Mayer's relation here. Let us see. We have also used this for, in KTG we have talked about it, right? So let us derive it. Can I rub off the first column? So here, suppose we talk about Mayer's relation. See, dq equals du plus dw or du plus pdv. This is your FLT. I divide throughout by n dt. dq by n dt equals du by n dt plus pdv by n dt. I write like that. I divide throughout by n dt, and let me say I'm talking about an isobaric process. How do I represent that? By putting a subscript like this, P. Now this, by definition, is Cp. This, whether you say or not, it doesn't make any sense to say this for du because du is a point function. Anyway, this will be Cv. And now we have to get this. Look here. If it's an isobaric process, what will be the value of dp? dp is 0. So if dp is 0, what do you get pdv by n dt as? Well, that's it. That's a derivation for Mayer's relation. So we'll write that down also because that's always valid. Things which are always valid, I'm writing here. We proceed.